Okay, we're back to finish up our notes on ramps, and we're going to look at a couple more involved cases this time. Last time we looked at a situation with a box on a frictionless ramp. Okay, the ramp had absolutely no friction acting on it. And the forces, there was only two of them acting on that box. It was the force of the normal force. Well, that's the force from the surface of the ramp that points perpendicular to the ramp surface. So kind of up, but at an angle, not straight up. And there's also the force of gravity, which points straight down, which we had to break into components. And that's where the trickiest part of this came in. We had to break this into components. Now we're going to add in a couple different situations. What if now the box slides on a ramp that has friction on it? What if this ramp does have friction? Okay, it's not frictionless anymore. How does that change the situation? Well, the first thing I think I would do is let's think about our axis again. Okay, remember we tilted our axis so that we could line the x and y directions up with the direction that's parallel to the ramp surface and also perpendicular to the ramp surface. Okay, that's how we set this up. If this box is now sliding, okay, let's imagine we put it on this ramp. Let's imagine that now the ramp has friction on it. What direction will the force of friction be? Forces are vectors, so friction has a direction to it. Without friction, this box would tend to slide down the ramp, right? Well, if friction opposes motion, that means friction should point up the ramp in the negative x direction. Remember, negative x is just indicative of our axis here. I could have very easily made my x direction positive in this direction, but I chose not to. Not for any particular reason, just because that's what I wanted the axis to be. Does having friction change the magnitude or direction of the normal force? Does having friction on there change how much the ramp pushes on the box in this direction? No, it shouldn't. Does it change the magnitude or direction of the box's weight? Does it change how Earth pulls on the box? No. But will the net force change due to the addition of another force? Absolutely. We're throwing another force in there that's going to alter our net force and our net force equations. Now, let's think about some of the possibilities for the motion of this box. Before, in the last example, we had the box, it was just going to accelerate down the ramp because there's nothing holding it back. Now that there's friction possibly holding this back, there's a lot of different possibilities for this. Okay, I could see a case where friction is not very strong, it's not a lot of friction, and this box, so the friction is very, very little, it's a very small force, the box still accelerates in the positive x direction. I could see that happening. I could see a case where friction and the force of the component of the force of gravity pulling the box down the ramp are exactly equal, or they're matched to one another. So I could see this box moving down at a constant velocity if it's already moving. I could see a case where friction is much stronger than the component of the force of gravity trying to get the box to move down the ramp. So I could see a case where the object accelerates in the negative x direction. And again, remember, accelerate does not mean move. Accelerate in the negative x direction just means that, well, the acceleration points back up here. This box there's nothing that's pushing the box up, okay? Friction can't make the box move up this direction. So if the box is already moving down the ramp and it accelerates up the ramp, that would mean it slows down. Okay, so that's a possibility. Nothing's going to make the box move up the ramp based on just these forces. So it could accelerate in the positive x direction. It could have a constant velocity as it moves down. I'm going to add that in. Moves down with a constant velocity. It could accelerate in the negative x direction if it was already moving. You could even have a situation where if the box was motionless to begin with, friction matches the component of the force of gravity trying to pull it down, and it just remains stopped. It never moves. So just adding in friction brings out this wide variety of things that could happen that all depend on the initial condition of the box, whether it's moving or not, and how big the force of friction is compared to the component of the force of gravity trying to move it down the ramp. let's draw a free body diagram and write out our net force equations for this situation. Now, I'll try and draw this big so you can see it. And I'm going to go over the logic of everything as well again. So here's our dot. We're going to label it box. Let's draw the, we need an axis. So here's our axis, just like before, just like up there. X, Y, plus minus. And let's draw our forces. Let's start with the two that were on the box last time. There was the normal force, perpendicular to the ramp surface. Ramp surface is angled, so the normal force is at an angle. There's the force of gravity, straight down. Okay. Notice the normal force is in the positive y direction. Force of gravity is kind of in between. It's in the positive x and negative y directions. And we said that friction, if it's acting on this box, will act to oppose motion. The box would definitely slide down the ramp if there was no friction. Friction opposes that. Friction must point in this direction, up the ramp. You'll notice that that's the negative x direction. So notice that Fn and Ff are aligned with my axis, Fg is not, therefore I must break it into components. If you tilt your head, you can kind of see that Fg is kind of in the positive x direction and kind of in the negative y direction. It's in between. So here are my components. Okay? If you remember from last time, the angle theta, which is important for determining whether this is Fg cosine theta or Fg sine theta, will always go between Fg, the downward force of gravity, and the component that is perpendicular to the ramp surface. My ramp surface is in this direction, okay? Aligned with the force of friction and this component. This is the component that's perpendicular to the ramp surface. Theta goes between the downward force of gravity and the component that is perpendicular to the ramp surface. Theta goes right here. And if this component is right next to where theta is, it's adjacent to it, and the trig identity that has to do with a side that is adjacent to an angle is cosine. So this is Fg cosine theta. This must be Fg sine theta. All of those things need to be in your free body diagram. I know I just spent like 2 minutes talking about that. The more you do ramp problems, the easier this will get. It is something that you have to practice. Very few people can just look at this the first time and say, I got this. You have to practice this. Writing the net force equations. F net x. Let's start with the forces that are in the positive x direction minus the forces in the negative x direction. That would be Fg sine theta, force of gravity, times sine of theta, minus the force of friction, equals max. F net y is going to be Fn minus, that's in the positive y direction, Fg cosine theta, equals may. Notice that I never had just plain old Fg in either of these because that's not in the x or y direction. The whole reason we split Fg into components is so that we could write net force equations. I'm going to work through the net force in the y direction right now because I know that this box is not going to accelerate up off the ramp or down into the ramp. So ay must be 0. Therefore, Fn and Fg cosine theta are equal, and I'm going to keep turning Fg into mg where it is appropriate. Okay? I know that the force of gravity is equal to m times g. That's right in the reference tables. It's always true. Therefore, I can write this. Fn equals mg cosine theta. Okay? So I'm adding this to the other side, and I'm changing Fg, f of g, or f sub g to m times g. Let's move on to the question. What must the minimum coefficient of static friction be to keep the box from accelerating down the ramp? All right, so we don't want the box to accelerate. That's telling me that the acceleration is 0. And static friction means that it's not moving at all. So if I have Fg sine theta minus Ff equals max, and ax is 0 because there's no acceleration, we're keeping it from accelerating, then that means that Fg sine theta must be equal to Ff. If there's no acceleration, the forces are balanced. I can change that Fg into an mg minus, and since we're talking about the minimum coefficient of static friction, the smallest that mu can be, we're also talking about the maximum force of static friction. And that's useful to us because the maximum force of static friction, we can calculate that given this equation, mu Fn. Now, one thing that I want you to notice is that we already solved for Fn. Oh dear, I made a huge mistake. That's not just mg, that's mg sine theta. My bad. We know that Fn is mg cosine theta. So watch what I do here. Mg sine theta equals mu. I'm going to plug in my equation that I just found for Fn. I found this. I derived this from my free body diagram, okay? Nothing in the reference tables will say this. I found it based on my knowledge of physics and math. We're going to plug in Fn down here. Mu mg cosine of theta. It says I'm looking for the minimum coefficient of static friction. In other words, I'm solving for mu. So what happens if I divide mg cosine theta to the other side? Well, you might have noticed that this makes it so that we have mg over mg, and then sine theta over cosine theta. I can divide mg by mg. They just cancel out. Sine over cosine, you might remember from math class, is equal to tangent. So, interestingly, look what happens here. I haven't plugged in a single number yet, and yet I've found a way to determine what mu is. Because guess what? This theta, that's the angle that the ramp makes. I have that angle. It's 30 degrees. I just solved for a coefficient of friction. I didn't solve for the force of friction. I didn't solve for the normal force. I rewrote those equations in terms of other things. And so what I found was that mu must be equal to tan theta. That is not something anyone would have expected before doing this problem, yet the math shows that it must be true. Tangent of 30 degrees is 0.577. So I found the smallest coefficient of friction possible to keep this box in place. So, I mean, that can be useful. If you want something, if you have a ramp and you want something to stay on it, and you know what angle you want the ramp to be at, you know what the coefficient of friction must be between your two surfaces to get it to stay there. Okay, the smallest coefficient of friction. If I have a bigger coefficient of friction, this will still work. Okay, but that's the smallest possible coefficient that works in this scenario. So another interesting thing that happened here is if you had tried to plug in, if you had tried to use FF equals mu Fn, okay, and you had wanted to calculate the force of friction, and you had wanted to calculate the normal force, you would not have been able to do that because I never gave you a mass for the box. Doing this and working with just letters and symbols without numbers is called symbolically answering something, okay? Symbolic notation, or another way, there's a couple other ways to say it, but that's the one I say a lot, okay? You've just solved this symbolically. That's sort of useful. It's useful in Regents to be able to solve things symbolically. It is really useful in AP to learn how to solve things symbolically. The reason being is if you solve something symbolically, all you got to do is plug the numbers in at the end. You don't have to plug the numbers in throughout, and you don't have to do a whole bunch of calculations except for at the end. The other reason that this is important, and another thing to call this is a general solution, is that now, if I want to change the ramp angle, I realize that that's really the only thing that's going to affect mu, the minimum coefficient of friction. So let's say, I solve this and I see that mu has to be at least 0.577. Someone could then come along and say, okay, well, I have a 60-degree ramp. What's the minimum coefficient there? If you wanted to solve all these things through numerically, you would have to do all your calculations again. If you're solving symbolically, on the other hand, all you do is say, okay, I'm going to plug 60 in here, and that'll give me the same answer because the situation is still pretty much the same. So this is your first exposure to a real symbolic answer. Again, it's going to come up a couple times here where it's useful, in this class I should say, where it's useful to go through the derivations and get a symbolic answer. It is going to be very useful if you take AP Physics, okay? And AP Physics is not all doing algebra like this, but there is some of that involved, and trust me, you'll understand and appreciate even more the usefulness when we get there. Let's do one more example with ramps. Oh, I'm sorry, didn't even do this yet. So this is part of the last problem. If instead the box begins to slide and accelerate down the ramp at a rate of 2.5 meters per second squared, what must the coefficient of kinetic friction be? Let's go back to our net force equation for the x direction. It was FG sine theta minus FF equals MAX. Let's copy that down here. FG sine theta minus the force of friction equals MAX. Okay. FG sine theta is mg times sine theta minus mu Fn equals MAX. And again, we're going to take Fn from what we had before. You can flip back and look, but Fn in this case was mg cosine theta equals MAX. Now you're about to go plug in. You might be like, wait a second, we don't have a mass. That's not a problem because look at this. We have a mass in every single term. If you have a mass in every single term, that means if you divide every single term by m, it'll cancel out. So I'm left with g sine theta minus mu g cosine theta equals AX. Well, we know that g is 9.81 meters per second squared times the sine of 30 degrees minus mu, g is 9.81 meters per second squared, multiplied by the cosine of 30 degrees equals our acceleration, 2.5 meters per second squared. I'm trying to solve for mu, okay? So the first thing I'm going to do is I'm going to, let's see here, I'm going to do 9.81 times the sine of 30 degrees. I get 4.905. I'm going to subtract that from 2.5. I get negative 2.0 or 2.405. I'm going to write this down here. Negative, oh, and actually let's multiply these two. Cosine of 30 times 9.81. Negative mu times 8.495. Let's do 8.496. Equals negative 2.405. To get mu by itself, I divide by negative 8.496. We come up with a coefficient of friction. If we want this to accelerate down the ramp at 2.5 meters per second squared, the coefficient of friction that would cause this is 0.28. In other words, that's the exact coefficient if we wanted to accelerate at that rate. Maybe you wanted to slide down at a certain speed, or we wanted to have a certain speed by the time it hits the ground. If the coefficient was higher, you could predict that the acceleration would be less. If you wanted it to accelerate at a greater rate, you could predict that the coefficient would be less. Wait, I might have mixed that up. If you want the acceleration to be less, pick a bit greater, get a greater coefficient of friction. If you want the acceleration to be bigger, get a smaller coefficient of friction. Anyways, we'll move on. Our last example is pretty much as complicated as this can get in Regents, as far as ramps go. Let's say that the ramp has friction on it, and there's also a man trying to push the box up the ramp. Let's assume that the box has a mass of 50 kilograms, and the man pushes with a force of 400 newtons. If he's only able to move the box up the ramp at a constant velocity, what's the force of friction on the box? I immediately go to draw my my free body diagram. Here's the box. Since the box is moving up the ramp, I'm actually going to do this time. I'm going to do my axis like this, xy. I know that the normal force is perpendicular to the ramp's surface in the positive y direction. I know that the force of gravity points straight down. I know that's going to get broken into components. Since the box is being moved up the ramp, friction must be against that. Friction must point down the ramp. So this time, friction is in this direction. And the man is pushing up the ramp, so the applied force must be in the positive x direction. Okay, FA for applied force. Now again, notice, all of my forces are lined up with this axis, except for the force of gravity. Force of gravity is, if you tilt your head, kind of in the negative x direction, kind of in the negative y direction. Look at this. We have a component and another force in the same direction. That doesn't mean they're the same force. It doesn't mean they're equal to each other. It doesn't mean the force of friction is the component of the force of gravity. Sometimes I have people telling me that. No, it's just two force vectors in the same direction. Okay, there's nothing to it more than that. The force of gravity is somewhat in the negative x direction, so we need to represent the component of the force of gravity in that direction. Fg, Fg. This is the component that is perpendicular to the ramp. Here's the ramp. This is the component perpendicular to it. Theta goes there, which means this is Fg cosine theta. This is Fg sine theta. My net force equations. In the x direction, positive x direction is Fa. Negative x direction is Ff. And Fg sine theta. So minus Ff minus Fg sine theta equals MAX. I'm looking for the force of friction on the box. Oh, I guess I'll write the y direction just in case. It's always a good idea to write both directions off the bat, just in case you need both of them. We do know that this box is not accelerating in the positive or negative y direction, so I'm going to take this AY, make it 0, Fn equals mg cos theta. If I'm solving this for FF, that means I need to get FF by itself. And I'm told that the box is moving at a constant velocity up the ramp. That means no acceleration. So I'm going to add FF to the other side. Fa minus Fg sine theta, I could rewrite that as mg sine theta, equals Ff, the force of friction. Do I know what Fa is, the applied force? Yes. Do I know the mass now? Yep, 50 kilograms. Do I know g? Do I know sine theta? 30 degrees. I have all the tools I need to solve for Ff. 400 newtons minus 50 kilograms times 9.81 meters per second squared times sine of 30 degrees equals Ff. The force of friction must be, let's do this first, 50 times 9.81 times sine of 30, 245.25. I get that the force of friction on this box, if this is the case, is 154.75 newtons. Notice that friction plus the force of gravity, the component of the force of gravity pushing down the ramp, is exactly balanced by the man's up the ramp force. So what does that mean? That means that the box moves at a constant velocity. There's a lot of variations to ramp problems, but they all start from drawing an accurate free body diagram, making sure that the forces on that you've drawn are accurate, and then going from there. This is the toughest that the forces unit will get for you. Okay, this is the end of the forces unit, so this is the toughest it can get. If you're still lost on how to draw free body diagrams, I really suggest you go back and watch the videos. Okay, there's not some magic formula for coming up with these diagrams. It is logic and rational thinking. So if you missed something, if you're like, I don't quite understand that, go back and watch some of the first videos that we did on ramps and see if you can pick out what you need from there. If not, then feel free to ask questions, but just so you understand, this is a tough topic. It's not something that you can that most people can get by just, watching it once. You have to practice this a couple times. So don't get discouraged if you don't quite get it yet. With some practice, I'm sure you'll be able to. If you have any questions, again, please let me know. And our next topic will be gravitation, and then we'll move on to circular motion. And by that point, we'll actually be pretty close to our midterm, if not quite at our midterm yet. With all that being said, hopefully this was a good video. Let me know if you have questions. I'll talk to you later.